thin wire consists of a semicircular arc of radius r joined tangentially to two straight semi-infinite wire segments, all lying in the plane of the page. A steady current I flows through the wire in the direction shown here. Determine the magnitude and direction of the magnetic field at the center of the semicircle. Express your answer in terms of the current I, the radius r, and the magnetic permeability mu0. So to start, we can break this problem down into three parts. So by the principle of superposition, superposition basically states that you can take the magnetic field, the total magnetic field at this point here, is the sum of the magnetic fields of all individual sources. So if we divide this up, first let's divide this up into three major pieces. So we have the infinite wire, semi-infinite wire on the left side, the wire on the right side, and the semicircle. So these are our three main pieces. So we can take it apart and add the total magnetic fields from each of these three segments. And so let's start by figuring out what the magnetic field of this wire is here. So to find the magnetic field, we can use the Biot-Savart law. And that says that its little magnetic field is equal to mu0, the permeability, over 4 pi times I dl cross r hat over r squared. So here, let's start with this wire here. So to make it simpler, I'm going to draw it like this. So let's say the point is here, and then we have a wire, and we have some current going through. It doesn't matter which direction the current is going. If you use the right hand rule, if it goes this way, then it will end up pointing out of the page at the point. And if you do it the other way, it will go into the page, since both the point and the wire are in the plane of the page. So if we draw it like this, and let's say we pick a random element, say this one, and this has a current I going through it with a length of dl, and dl points in the direction of the current. And so then this length here is r, and r hat is a unit vector pointing towards the point that we want to find the magnetic field. So the unit vector is just points towards the place where we want to find the magnetic field. And as a unit vector, it just has a magnitude of 1. So we can simplify this a little. If we recall that if we have two vectors, A and B, and we want to take the cross product of them, that's simply equal to the magnitude of A times the magnitude of B times the sine of the angle in between them. So this is the angle between them, and it doesn't matter if you pick the larger angle or the smaller angle. So if you have two vectors like this, then you can pick either this angle or this larger angle as well. And it doesn't change the math. So with that, we can write this more simply as mu0 I dl and then let me define the angles here. So I want to define this angle here as theta, but here the sine of the angle is actually the angle between the two vectors in the cross product. So it's the angle between this dl vector, which points this way, and the r hat vector, which points this way. So we want this angle here. So we can just we know this is a right triangle since this part is perpendicular. So then this angle here is just going to be 90 minus theta degrees. And we want the angle between the two here. So then we can just, it turns out if we use the sine of this angle or the sine of this angle, they will actually be the same. I think there's an identity that says that the sine of 180 minus theta, I'm going to use a different letter just so we don't confuse it with this theta here. But basically what this is saying is it doesn't matter if we use this side of the angle or this side. Either way will give the same result. So we will pick this side for simplicity, and this angle is given by 90 minus theta. And we use this angle because it's the angle between the vector dl and the unit vector r hat. It's not this theta here. That's a different angle. So with that in mind, we can write sine of, I'm kind of running out of space there. Let me write it down here. So that becomes dB equals mu naught I dl sine of the angle between them, which is 90 minus theta, over 4 pi r squared. And here we drop the vector sign because we know that it's going to be either pointing out or into the page, and we are only going to find the magnitude, since for each dl element, it's in the same plane as the place where we want to find the magnetic field. So this will, we can drop the vector nature and just see where it points by the sign. If it's like positive, it will point one way, and if it's negative, it will point the other way. So we can just write it like this. And now sine of 90 minus theta, you can use trigonometry, and that's just equal to the cosine of theta. So we can replace that there. And now we want to either write everything in terms of theta or in terms of x. So one more thing. Let's call the distance from the start, let's say this is 0. Let's call that distance x. And this distance is going to be r, because if we look over here, this is like, this distance is r. And that corresponds to this distance here. So we can either write dl and r in terms, we can either write dl, r, and cosine theta all in terms of x, and then do the integral over all of the little magnetic fields to find the total one. Or we can also choose to do it over theta. And it really doesn't matter which one you do, you'll always end up with the same answer. But it is slightly easier if you use the angle theta here. So let's write everything in terms of theta. So in this case, the dl, each little length is just dx, since we've chosen this line to be along the x-axis. And then from trigonometry, if we find the tangent of theta, that's going to be equal to the opposite over the adjacent. So that's x over r. And then we can solve for x to get that x equals r tan of theta. And now we can differentiate both sides. So if we do dx d theta, that's equal to, r is just a constant, it's the radius. And the derivative of tangent of theta is secant squared of theta. And then we can just simply rearrange this to get that dx equals r times the secant squared of theta times d theta. So now we have an expression for dl, which is the same as dx, and we can plug that into there. And it's all in terms of theta. So Let me erase this a little so that we have more room. Fine, copy. dl equals dx equals r secant squared of theta d theta. So now we have this part down and we can sub it in. Now we also need to find what this distance r is in terms of theta. So if we can, this is a right triangle, so we can just use the Pythagorean theorem to find r. So that gives us that r squared is equal to r squared, big R squared, plus x squared. And we just found earlier that x was equal to r times the tangent of theta, because tangent of theta is x divided by r. So we can plug that in for x. So we get r squared plus r tan theta squared. This becomes r squared plus r squared tangent squared of theta. We can factor out the r squared. So we get r squared times 1 plus tangent squared of theta. And 1 plus tangent squared of theta, there's a trig identity that says that this part here is equal to the secant squared of theta. So now we have both r squared and dl in terms of theta, and we can now plug that into the expression for dB. So let's do that. So then dB equals mu naught I. dl is r times secant squared of theta d theta. And then sine of 90 minus theta becomes cosine of theta. And then it's divided by 4 pi. And then r squared we derive to be r squared, big R squared times secant squared of theta. Okay, so I'm going to clear up this area up a little. And now we have our expression for dB. So dB equals this. So now to get the total magnetic field from this semi-infinite line, to find its magnitude, we just integrate and sum up all of the little magnetic fields from each point along this. And again, this is just basically one application of superposition, where the total magnetic field from this line is just the sum of the magnetic fields of all of the little tiny elements of the line. So this becomes an integral. We can just plug in the expression we found for dB. So we can just plug in all of this here. I'm going to simplify this a little. If we see here, you have secant squared theta in the denominator and the numerator, so they cancel. And also the r, one of the r's cancels, so this cancels, and the squared disappears. So we have mu naught I cosine theta is still there, d theta, and in the denominator we still have 4 pi r. And now notice that this integral is in terms of theta. So we need theta bounds for our integral. So now if we take a look at this picture, if we see how we've defined theta, let's draw the two scenarios. So at the start, we're basically starting over here. We want to get the very first little element of the line here and figure out what its magnetic field is. So initially, our theta will be very close to 0. So we want to start at theta equals 0. And then if we imagine what happens at the end, let me erase this. So here's our line, the current. So we add up this little area, and then we add up the magnetic field from this little segment, and so on, until we go all the way to add up the magnetic field from the segment that's almost infinitely far away. And at that point, your angle theta is going to be very large, and it's going to be approaching 90 degrees as you try to add up the magnetic field from the piece infinitely far away. So at the end, our final theta approaches 90 degrees, which is pi over 2 radians. So that will be the upper bound of our integral. So now we can just integrate this here. And in terms of theta, it's a pretty simple integral. You can just mu naught I, 4, pi, and r are all constants, so they can be pulled out. And then we have our integral from 0 to pi over 2 of cosine theta d theta. The integral of cosine of theta is sine of theta. So this becomes mu naught I over 4 pi r times the sine of theta. And we evaluate this from 0 to pi over 2. So this becomes sine of pi over 2 minus sine of 0. So sine of 0 is 0, and sine of pi over 2 is 1. So this finally just evaluates to mu naught I over 4 pi r. And that is the magnitude of the magnetic field at this point that is perpendicular to one of its edges. And that's the magnitude of it. And it's kind of interesting, is this because the magnetic field of a full infinite line at some distance r is this mu naught I over 2 pi r. So it's quite interesting that it works out to be exactly half. Okay, so now this can be used for both this line and this line. They are both they're both in the plane of this page here. So the magnetic field would be either pointing out or into the screen at this point r. And we can use the right-hand rule to separately find the direction later. But this expression here, it describes the magnitude of the magnetic field of both this wire and this wire, although separately. So each wire, the magnetic field from each of these two semi-infinite wires, has this magnitude. So that's one part of our problem done. Now we just need to find the magnetic field due to this semicircle. So let me go ahead and erase all of this here. And then I'm going to write here, just to note it down. The magnitude of the magnetic field due to the line is mu naught I over 4 pi r. Okay, so now let's do the second part of the problem. So now we want to figure out the magnetic field arising from a semicircle. And we want to find the magnetic field at this point at the center. So we can do something very similar where we add up the magnetic field due to each little segment of wire along this circle. And again, the magnetic field will be either pointing into or out of the page at this point here. So if let's define this angle here as theta. Now notice that for each theta, it doesn't matter where in the circle. By the definition of a circle, the radius is always perpendicular to the tangent on the semicircle. So there's always a 90-degree angle here. And this tangent is the direction of dl at every point, since that's where the current is flowing. If you take, for example, this point, the current will be flowing along here. If you take this point, the current will be flowing tangent to it. So there is a 90-degree angle everywhere between the radius r and dl. And if you notice, r hat will be this little vector here. Okay, it might be a little hard to see there, but so let's say that this is dl for this point, and this is r hat. And that's the unit vector pointing towards the point you want to calculate the magnetic field at. So because of that, the angle between, let's call this phi the angle between dl and r hat. So that's always going to be equal to 90 degrees for all points on the semicircle. So that means that the sine, if we remember from this Biot-Savart law, that means the sine of the angle between them is always just going to be the sine of 90 degrees. So this will always just be, oops. This will always just be the sine of 90 degrees. And the sine of 90 degrees is always 1. So this term we can just ignore basically. And that makes it a lot simpler. And again, we need to find a way to express dl and r squared in terms of either constants or our variable that we're integrating with respect to. So for this case, let's integrate with respect to theta again, since it's pretty clear that we start, if we define theta to be the angle from this line here, then at the start, theta will equal 0 degrees. And at the end, when it sweeps all the way over there towards this other end, then theta is equal to 180 degrees, or pi radians. And we want to integrate all of the contributions to the magnetic field from all of the elements here. So each element dl. So we need to figure out what dl is. So let's start with one relation here. We know that for a circle, if theta is measured in radians, then the length along the circle is equal to the radius r times the angle theta from the horizontal in this case. But here, to use this, theta must be in radians. So if we use this relation, then we can differentiate to get that dl d theta is just equal to r. So then dl is equal to r d theta. And also, it doesn't really matter here, but probably should have used L just to keep things consistent. So we can use this relation to plug in something in terms of theta. And also, we also have to figure out what r squared is. Now the nice thing is, since it's in a circle, the distance from each of these current elements to the center point is just r. So the radius squared is, little r squared is the same as big R squared in this case, which is a constant. So now that we have all of that, we can plug it back in to get an expression for dB. So if we plug that in, comes mu naught over 4 pi times I. dl is r d theta, and r squared is this big R squared. I'm just going to erase this to make more space. that's dB. And if we notice, we have big R both in the numerator and denominator, so we can cancel one of them. And so now to find the total magnetic field, again, we just sum over all of the dBs, all of the little magnetic fields from each little point, each little current element. So the total magnetic field is integral of dB, and this is just the integral of mu naught I d theta over 4 pi r. And as we said earlier, we're integrating from theta equals 0 to theta equals pi. Since we're starting here, we add up this little bit and this little bit and this little bit and all the way up to this little bit here, the magnetic field from this little bit. And we have this expression now after plugging dB in. And now notice how almost all of these are constants. The permeability is constant, the current is constant, 4 pi is constant, and the radius r is also a constant. So since they're all constants, we can pull them all out of the integral. And just integrate from 0 to pi, integrate d theta from 0 to pi. So this is just summing up all of the little theta pieces, and so this just becomes theta, the full theta, and we evaluate it from 0 to pi. And if we plug that in, that becomes pi minus theta. So theta equals pi minus theta equals 0. And so our final answer becomes that B equals mu naught I over 4 pi r times pi minus 0, and so we can ignore this part. And the pi cancels out, so we get that it is equal to mu naught I over 4r. And that's the magnitude of the magnetic field due to the semicircle. So now we have all of the part pieces needed to solve this problem here. And you go ahead and organize this again. So we just derived that the magnetic field magnitude of the semicircle is equal to mu naught I over 4r. And so now again we use the principle of superposition, and we can find the magnitude of the magnetic field for this line, and for this semicircle to find the total magnetic field. And we also need to pay attention to direction here, since the magnetic field is a vector. But they're all in the same plane as the point you're looking at. So the magnetic field vector will always be perpendicular to the plane containing the wires and the point that you want to find the magnetic field at. So in all three of these cases, the magnetic field will be either pointing into the page or out of the page. And we can simply add them like scalars if we assign a negative value to, say, pointing into the page. So now, if we use the right-hand rule for this segment here, we will see, and the direction of the magnetic field, we can just use dl cross r, and we can figure out what direction this is in. Like, we can pick any little current element here and figure out what direction the magnetic field. We can do dl, that's there, cross r, and if we do that, that turns out that this will be pointing into the page. So it's going to be like that. It's kind of hard to see, but let's say I draw. So this will have a magnetic field pointing into the page. Now let's figure out for the semicircle. Again, if we do the right-hand rule, it's also going to be pointing into the page from the semicircle. And then from the other side of the wire, this other semi-infinite wire, that's also going to be pointing into the page. So all three of the magnetic field vectors will be pointing into the page. So we can just sum their magnitudes. So that's the magnetic field magnitude from the line. You can add it to the one from the semicircle and add it again to the other one from the other line. And they're all pointing in the same direction. So the direction of the total magnetic field is going to be pointing into the page. So now let's figure out what the magnitude is. So all we need to do now is just plug in our values from earlier. First simplify this to 2BL plus BSC, which is semicircle. So now we just plug in the magnitudes we derived earlier. Then so this is from the semi-infinite line, and this is from the semicircle. And we can pull out mu naught I over 4 pi from, over 4r from each. So this becomes, we still have a 2 here, 2 over pi plus 1. And so that is the magnitude of the total magnetic field, and its direction we established earlier is going to be pointing into the page. And that is how you would solve this problem here.